A friend of mine gave me a link to a video offering 200 so-called proofs that the Earth is flat. There are many good videos explaining why it isn't. The main thing that those people who believe these things don't understand is how accurately we can measure the physical world these days and how well these measurements fit with the mathematical models of the world devised by real scientists and mathematicians. The ancient Greeks figured out that the world is round, and one of them, Eratosthenes, some 2,300 years ago, worked out the length of the perimeter of the Earth, the circumference of the round object, with the simple geometry we learn in secondary school. So I think nearly everyone will be able to enjoy and understand this short video. History. Alexander the Great conquered much of the world known to the learned Greeks of his day, not China and of course not America. He conquered Egypt, and a community of scientists and scholars grew up around the famous library in Alexandria. In Egypt, the temple priests for centuries had accumulated knowledge of geography and astronomy. People spent much time watching the stars at night and the shadows by day. Anyone can see that the sun and moon are round, and simple observations led people to believe that the Earth was round as well. For instance, when ships disappear over the horizon in any direction, the hull disappears before the mast. The horizon of the sea is only a few kilometers away, and anyone with good eyesight can confirm that this is the case. If the Earth were a geometrical plane, then ships would simply disappear suddenly if they fell off, or they would disappear by getting smaller and smaller and smaller. Secondly, sometimes the shadow of the Earth, passes across the moon, a lunar eclipse, just as sometimes the shadow of the moon passes between the Earth and the sun, and we have an ordinary eclipse. But the shadow of the Earth on the moon is curved every time. So from facts such as these, it was inferred that the Earth is a round ball like a sphere. Without being able to settle the question of whether we live in a geocentric or heliocentric solar system, the mathematicians of Alexandria estimated that length of the circumference of the sphere, and the best one was made by Eratosthenes. So, to study the shadows, the Egyptian priests and the scientists at the University of Alexandria used obelisks. Every city in the world seems to have one of these obelisks, perhaps as an homage to the great builders of ancient Egypt. Cleopatra's Needle on the north bank of the Thames is covered by hieroglyphs. These hieroglyphs often record the military victories of the pharaoh and his empire over his neighbours, not the defeats, of course. But the obelisks have another purpose: they cast shadows. For that, Cleopatra's Needle is not much use, but if we go to St. Peter's Square in Rome, we can see an obelisk being used for its original purpose. We can see a shadow here. Now we call it a square, but in fact it's round, it's a sundial. And you can see that as that is due east, then the sun at this time of day is over in the southwest, and as it's a long shadow, one might suppose it's well on into the evening of the day. So that's what the shadow tells us. But if you go to St. Peter's Square and you look just here along this line, you'll see a plaque. And that marks the point, which is where the tip of the shadow at noon on Midsummer's Day lies. It's marked there, you can see it for yourself. And there's another plaque further down here where you can see where the tip of the shadow at the winter solstice on the shortest day of the year at noon lies. So that's some simple geometry. And of course, if you can measure that length there, then you've got a triangle and you can measure the angle at the top. Either you can, if you've got that length and that length, you could make a scale drawing and measure the angle with a protractor, or you could use the tangent ratio or any other of the trig ratios to find out what that angle is. Now we need to know one more thing before we look at what Eratosthenes did, and we need to look at a map of Egypt. So here's Alexandria, and it was known that at Syene, now called Aswan, where the dam is, on Midsummer's Day at noon, the sun shone straight down to the bottom of a well and was reflected back. Now, just note this is the Tropic of Cancer, which is significant, and you might like to look it up. But so Eratosthenes knew that at that particular moment, on Midsummer's Day, the sun's rays were going straight to the center of the earth. But at Alexandria, they were still casting a shadow. So let's look at a little diagram, which is all we need to understand this. So this represents Aswan, and we can see here's the well. The sun is shining straight down the well to the center of the earth. The rays of the sun are all parallel. That's a good assumption. And there's the obelisk in Alexandria. And here's the shadow it casts. So Eratosthenes was able to work out that angle there was just over 7 degrees, 7.2. So by the alternate angle theorem, that must be 7.2 as well. More simply, that's 1/50th of the complete circle. That's a 50th of a complete turn. He also knew that this length from Alexandria to Syene was, in our units, 500 miles. So all he had to do was multiply 50 by 500, and he got 25,000 miles in our units, which is correct to two significant figures. So there's the simplicity of his method and the alternate angle theorem being put to good use. Now, when I was learning mathematics, to be a mathematics teacher, one head of department remarked, "Every maths teacher has to walk past 1,000 mistakes every day," which is pretty much true. But the fact there were so many didn't make any of them correct. And the fact that there are 200 so-called proofs that the Earth is flat doesn't make any of them true either. They have to be looked at one by one. And finally, this type of geometry would have been studied by all geometers and learned people down the ages. Certainly would have been studied by Isaac Newton as he continued to develop mathematics and worked on the calculus. And his remark is also pertinent, a remark when he said, "I can calculate the motions of the planets and the stars, but I cannot calculate the madness of men."